Now recording. So, how is everybody today?
Superb.
Superb. Lovely. How are things going? Are you enjoying the program so far? Except for networking. Yeah.
We called it. They kept it up. It's not
It's actually
Well,
worse.
It's the worst.
I mean, this isn't my first time teaching this semester in this program. I recall the, how do you want to put it? Very mild degree of spiciness that occurred last time around with respect to that course. And, I kind of anticipated that, if it was like that last year, probably going to be similar this year. History is the best predictor of the future, after all. But otherwise, other than networking, though, how are things going? Good. You finding the material stimulating?
I feel like this course is more stimulating than the best.
Sorry, this course is the most what?
I mean, this class is more stimulating than all the classes.
Oh, well, thank you very much. I try to make the class stimulating. Like you can see how using these building blocks you can produce a work that someone will pay for at some point in the future, right? It sort of leaves the territory of abstract knowledge and becomes something concrete and implementable. Something you might expect to learn in a college, even if you're doing a bachelor's degree. Well, hopefully we can continue this trend. So for today, we have basically, similarly to last week, my objective this week is to prepare you for the lab at the end of the week. So there are a couple of things that we need to have lessons on, and that starts with vectors. So, can anybody tell me what a vector is in a mathematical sense?
In a mathematical sense, a vector has a direction and a unit of measurement.
Okay, so we've got a direction and some kind of unit of measurement. So, in this description, there's like a word that I really need to hear to complete the description.
A line. So it's a big line.
New. It starts with an M.
Movement?
Nope. M-A.
Mass?
Nope. M-A-G.
Magnitude.
Magnitude, yes. Direction and magnitude.
That's what I meant by measure.
I figured that was probably what you meant by that, but technically speaking, all you're saying there is that we are measuring, we have some way of measuring it, which is true and necessary, but, generally speaking, when you talk about a vector, you're talking about some distance in some direction, right? So, for example, we might have an origin point, right? Some distance along some distance along some direction from one point to another, right? Say, for example, from -4, -3 to, let's put that right on there. -2, or 0, -2. 0, -1. 0, -1. All distance is approximate, right? So, there are two different ways of expressing vectors. One is magnitude and direction. What's the other one? another way to say this is r theta, right? It gets more complicated in 3 dimensions, obviously. So we can also express a vector using components, right? So a vector is also expressible as a collection of x, y components. One component for every dimension that the vector is in. So in here, we would have x, y, z, right? That is a vector. Now, the vector may have an origin point, right? So, you know, origin point can also be expressed as these components, right? So, you know, if we have 3, 3, and from point 3, 3, we have a vector, you know, -1, 2, then we go -1 in the x direction, so and +2 in the y direction, so that also expresses the vector. You can convert freely between the two of these using what branch of mathematics? Nope. Starts with a T. You learned it in high school? Yes. Trigonometry, that's right. Because if I have a 1 here and a 2 here, how do I get that angle theta?
Squared it.
If we have these two components, right, we don't have the hypotenuse, right? We could solve for it using, how do you solve for the hypotenuse of a triangle? Someone say it louder, I can't hear over the fan.
A squared plus b squared.
What's the name of the theorem? Yes, Pythagorean theorem. So we could solve for the hypotenuse, but it's easier to just use the only trigonometric relation which does not require it, which is tangent. Right? So, vectors. In here, the vectors that you use, and you'll probably have gotten this impression already, the vectors that you will be using are component vectors primarily. However, as we are going, one of the things we are going to do is draw rays. Now, can anybody tell me what a ray is? Yes? A line going in a certain direction. Well, yes. So you've got basically 3 different. You've got 3 different types, right? All of them, all lines, all of the various types of lines can be defined by 2 points in space. You've got a line that goes between 2 points, right? You've got the line that goes between 2 points and off to infinity in either direction. And you've got the line that starts at a point, goes through the other one, and continues to infinity in one direction, right? This is a line. This is a line segment. And this is a ray. Anybody heard the term ray casting before? So, ray casting is an operation that you perform to find the intersection of virtual geometry with a ray. Raycasting is used by the game engine's renderer to determine what color a particular pixel should be during rendering, for example. So what the game engine actually does is it casts a ray from the main camera, sends it out into the object, into the level geometry. If it intersects something, it samples the color of that thing at the point it intersected it. Sometimes it does more complicated math as well, but it reports the color of the thing the ray hit back to the camera. That's how it decides what color that pixel should be, because it performs ray casting. And, quick question, see if anybody plays video games. What happens if a ray does not intersect any of the level geometry? What do you get? Say a little louder.
No clipping?
No clipping? No clipping is when you turn off collisions. Not quite the same thing. It is a type of texture. No. So let's visualize it. Let's say we have level geometry, right? We have our camera looking more like that, sure. We cast a ray, it strikes level geometry. This is good, it renders the geometry. What happens if it passes above level geometry or through level geometry and just continues off into space? What do you get? What does the game engine put there for the pixel value? It is a skybox. So if the ray does not collide with any of the level geometry, instead it picks a pixel from, it picks an appropriate pixel from the skybox. So that's how rendering works. Does that make sense? Sort of. So let's talk for a moment about unit vectors. All right? So a unit vector, does anybody need any of this? Anybody want to take a picture? No? Okay. I'm going to erase it. So the draw ray method, which we will be using to draw debugging rays inside of Unity this very day. This method and other ray casting methods like to think of rays in terms of angle and magnitude. However, the entire Unity system is built on component vectors. So we have to find some way of converting between component vectors and angle magnitude vectors in three-dimensional space. The way that we get there is by specifying what's called a unit vector. So, because there are other ways of expressing angles. Quaternions are a way of expressing three-dimensional angles. Euler angles are the easiest one. It's just the angles that you know and love, but expressed 3 times instead of once. But another way of specifying a direction is to specify a direction without a magnitude. And the way that you do that is by using a unit vector. So let's say, just for the sake of argument, we wanted a vector that was going say vector is equal to 10, 12, negative 3. I almost put a semicolon at the end of that. A unit vector is one that has a magnitude of 1. Right? Is the magnitude of this vector 1? Obviously not. The x component alone has a magnitude of 10. So the idea that the whole thing has a magnitude of 1 is obviously ridiculous. So the question then becomes, how do we find the magnitude of a three-dimensional vector? Because we know how to find the magnitude of a two-dimensional vector. How do we do it in 3 dimensions? Right? For example, we have v2 equals 4, 8. Right? How do we find the magnitude of the vector? How do we find m? Pythagorean theorem. Magnitude is equal to the square root of the x component squared plus the y component squared. So, here is a handy little extension, all right, for working with magnitudes in 3-dimensional space. Because in 3-dimensional space, and I apologize, I'm not very good at these, you would have something like that, right? It turns out that Pythagoras, our old friend Pythagoras, if we want to calculate this, we can actually break it into two sub-triangles, right? The first triangle is composed of can be composed of the x and the y components. So if we call this, I did that way too small for anybody to back to be able to see, I'm sorry. Let me make it bigger. So x, y, z, right? If we want to position a vector, say, here on the z, here on the x, and here on the y, right? We can find the intersection. That's an unfortunate choice, because that's going to end up right on the y-axis. Let me pull it over here. Should be using different colors too. We can find, like if we consider only the x and z components, right? We can find this point with one application of Pythagorean theorem. We'll call that M1, right? So M1 is equal to Pythagoras as applied to x and z. X squared plus z squared. Okay, sounds good. If we add in the third dimension, we want to go a certain distance up, like this amount here. So we'll end up right about here. If we take a look, we end up with another plane in which a triangle can exist, right? So our actual vector goes from the origin to this point, which is the intersection of the three components. Right? So, if we call the magnitude here M2, and if we sort of pull it out of three-dimensional space and just look at the thing, we have M2 here, M1 here, and then this becomes our remaining unused component, Y. Right? So, we can apply our old friend Pythagoras once again. M2, I'm sorry about the green marker being faint. I'll do it in black. So M2 is equal to the square root of M1 squared plus Y squared. All of your algebraic brains should be just itching to perform that substitution. So we end up with M2 being equal to the square root of x squared plus z squared plus y squared. Now what do we know about square root and the square? That's right, they are inverse operations of each other, therefore they cancel each other out. So, it ends up quite nicely and simply, x squared plus y squared plus z squared. That gives you the magnitude of the vector. Which is not too bad, right? And the nice thing about this is that it also extends itself into n-dimensional space, but of course, being merely three-dimensional creatures, you know, this is usually as much as we need. So the question is, if this is now our formula for magnitude, how do we convert a vector into a unit vector?
So
Yes?
you use that operation, you know, x, y, z values. And
Well,
you get a unit vector, it'll be like something crazy. You multiply that.
So, the way that you can modify the magnitude of a vector is by multiplication, right? When you multiply, like, each of the components of a vector, you multiply the magnitude by that same amount, right? So, for example, if I were to say 2 times this amount, I would get a vector with a magnitude that was twice as much as well. This works in reverse. If I take our vector, there we go, and I multiply it by 1 over x squared plus y squared plus z squared, I have divided each of the components by the magnitude of the vector, thus arriving at a vector which, if you perform this same operation on the components, the magnitude of the vector will always be 1. A unit vector is a vector that has a magnitude of 1. Right? So, the formula then, if you want to expand it out, is x over square root x squared plus y squared plus z squared, comma, y over square root x squared plus y squared plus z squared, comma, z over x squared plus y squared plus z squared. I'm going to call it u for unit vector. So, is that making sense? So this is the thing that we need, like, this is the thing that we need. You now understand what it is, hopefully. And now I can gratefully tell you that Unity will automatically calculate a unit vector from any vector for you, as long as you've composed it using the vector class. So, let's see how to make something from the vector class. Because why would you need to do that yourself, right? You should understand the math, but you know, you don't necessarily have to do the math yourself every time. So, in our Unity, please make yourselves a new game object, whatever your favorite is. Just don't choose plain. Choose a three-dimensional solid. I think today I will choose a cylinder. There we go. Lovely. Let us attach to this cylinder a script. So, quick review of how to do that. Click on it so that you get the properties. Add component. New script. Vector fun. Create and add. There we go. Double click it to open it in Microsoft Visual Studio. Skip. Start. Wait for it to figure itself out. But don't wait too long. There we go. Is it going to open itself the first time? Probably not. Double click it again. Bing, bang, boom. So, good. So, this is a kind of a rough introduction, once again, to, it's like our second rough introduction to using objects and classes. So, a highly important class when using the Unity game engine is the Vector2 and Vector3 classes. The position, or the position element of the transform game component uses Vector3s in order to control the position of game objects, control the rotation of game objects, no less. So, we can declare our own Vector3s. Let's make it public. Vector3, my vector. Turn off. There we go. So, what we have done right here, we have declared a variable of type vector3. That is to say, a vector with 3 components. This has not yet created the vector. We have declared the variable, but we have not created the object. It's a little bit similar to declaring an integer, but not providing it a value, right? We have not provided a vector to be supplied here, right? So, let's do that. My vector, and this is inside of start, is equal to new vector3, and we can examine things a little further. Right now, we're not providing any further information about this vector3. This is object instantiation. We declare the variable up here of type vector3. Here, we have actually created the object. This room is kind of, the monitors are a bit too big in this room, I think. Yeah, like it would be so much easier if they just took them down off the towers. You know? You're welcome to bring your chairs to the front. I can't do anything about the level geometry, unfortunately. Yeah. Vector 2 only has 2 components, x and y. Vector 3 has 3 components, x, y, and z. You'll find that you very rarely, if ever, use vector 2s, even in 2D mode, as, even in 2D mode, Unity still maintains that third element in its positioning. So, so in Unity, it's kind of stupid, but this is how Unity decides to do things. If you have a 2D game that looks like, you know, hill, background, sun, something like that, the way that you, like the efficient way to do layering in Unity is to actually put these things on different Z levels, so that if you took like a side angle view, basically it looks like cardboard cutouts of like all of your scene. Or, you know, turn that sun so that it's angled towards the viewer. Right? That's what Unity does natively, so even in 2D mode, you can't get away from vector 3s, so vector 2s you hardly ever use them. Excellent question though. Any other questions? Oh, okay. So, our newly created vector 3 so far has not been populated with any data. So, if you take a look at the little slidey bar here, you can see there are 3 ways to initialize our vector 3. The most useful is to provide 3 floats, 1 for each component. You will find as you program in Unity, very often you won't be assigning these things to variables, you'll be creating them on the fly inside of a line of code. But for now, let's tie everything to a variable because that makes it a little easier to understand. So, let's say I want 5.23 float, 6.1 float, and negative 9.2 float. The reason, we've been through the little f's, right? Yeah. Quick recap, the reason these f's are necessary is, for some reason, floating point literals in Unity are by default of type double, and yet everything else uses float. Those are 2 different incompatible data types. If you want it to not complain, if you want the compiler to be fine with it, you have to specify this is a float and not a double, actually. So that's what the F is for. It's stupid, but you still have to do it. Save. So we now have our vector. If we pull ourselves back to the Unity interface, let it recompile that script, you will notice that, drum roll please, come on, there you go. You will notice that in the inspector, we get X, Y, and Z components showing up the same way that we do here in the position transform. So that's a fun little thing you can, basically it provides the same interface as it does up here because it's fundamentally the same thing. I think that the sharpness is incorrect. I think that the projector is, it's like fuzzy towards the bottom. Am I just crazy or is anybody else seeing that? It's a little fuzzy towards the bottom. Like look at the crispness of like this Unity icon versus that one, you know? Anyway, so if we run our program, you can see the start method populates the values which we set in the script. They are now visible on the exterior. Because this is a public variable, we can grab these and move them however we want. Make sense? So far, so good? So,
Sorry, what's this class about?
we're learning Unity.
Sorry, I'm just trying to take notes on all the classes that should probably take next year.
Oh, well, I don't think that you would be able to get into this one. This is for the Digital Health Bachelor's Degree program.
And how do you know I'm not one of those people?
Because there are only 10 people in the whole class. You can
Okay.
apply next year though, if you
Well,
want.
I'm just keeping my options open.
Okay,
I'm just trying to.
you're interrupting my class.
Sorry, I didn't mean to. Your door was just wide open. Well,
All right, well, I'll close it then.
Well, it wasn't wide open, but it was partially open. Sorry.
Thank you. I mean, I guess that means you found the class interesting. Maybe, I don't know. Get weird people. Like, human beings, man. Ugh. What was I talking about again? All right. What were we talking about? Ah, yes, I was going to do debug race with. Okay. So we have a vector. Basically, that means we have an object containing x, y, and z components instantiated as a variable. Now, everything's good. Our next step is to use this to create a debug ray. Debug rays are basically just lines that appear in your scene viewer, not in the game view, in the scene view. But these can be used for other things like raycasting, which is fun. So, it's fun, but it's a little complicated to get a good demo working for raycasting, so we'll just leave that to the side for the moment. So, debug.log, we've used quite a bit already. Log is a method of the debug class. Debug provides other useful things. Debug dot, you can see it's got quite a lot of things. Draw line, draw array, those are the ones we're interested in. Debug dot draw array. You can see our there's quite a lot of arguments here, but that's okay because without these, then like all of these make sense, right? So the first argument, start, is the starting point of the ray, right? Recall, if we're drawing a ray from one point to another, we need to know the point we're starting on. In this example, we were starting at the origin, right? Then we need vector 3 for direction. The direction will be the unit vector, which indicates the direction that the thing is traveling. Color, self-explanatory. Interesting one, duration. How long do you want this ray to appear on screen for? So, that being said, actually, I think I'm going to put this in start rather than update. Debug.draw ray. So you'll notice, draw ray has not, like, the one thing that it doesn't have is magnitude. We don't have to say what the magnitude is, right? And that, if you recall, the definition of array, you get the starting point, you get another point on the ray, and then it just continues off to infinity. So the default magnitude of a ray is infinite, right? So it doesn't need to be provided because it's always the same thing, and that thing is to infinity and beyond. So, sound good? Is everybody following all right with this? Any questions? Yes?
Why do you put it with a start with the
Because this thing has a duration. So if I put it in the update method, I would be drawing 60 of these per second, right? And if I set the duration to be less than 1/60th of a second, you wouldn't be able to see it. And they would, like, basically it's a recipe for having, like, you know, if I set the duration of the debug ray to be 5 seconds and I'm getting about 60 of them per second, you know, then I have 300 rays on screen simultaneously, all overlapping each other, and it's just not. Especially if I'm like swapping the colors around. Make sense? So, debug ray. First is our starting point. We could choose the origin. The origin would be a new vector 3, 0, 0, 0, right? But, because this is a script attached to an object, I'm going to take the position of the object as the starting point of the ray. That way, if the object is moved around inside of the space of the game, the ray is always attached to it, right? So, this dot transform dot position. Position. There we go. Now, we need our direction. Direction and length. Uh-oh. I think that the documentation might have lied to me. We'll see. So, my vector dot yes. So, unit vectors are also called normal vectors sometimes. So, my vector dot normalize of course, that is a method, so we will have to normalize the vector before passing it to the debug function. We can't just use this in here because the normalize function doesn't return anything. It's an operation on my vector. It normalizes it. Once it's been normalized, then we can use it as a normal vector. Now we can add a color. The quick way of doing that is something like color.red, color.blue, whatever you like. And then we have duration. So let's say, just for the sake of argument, 10 seconds. Question?
Always says if the little description equal to second.
Yeah, that's in seconds. So, let's see how it looks. Oh, I can't see anything. Because it's in the scene. There you go. you there for 10 seconds. There we go, see? There is our debug ray. And it turns out that they do want the magnitude, actually. So just get rid of the normalization. It must be the ray casting that requires the unit vector. I apologize, my brain was confused. So, in our scene, here is our vector. Going out like that. I'm going to set the duration a little higher. There you have it. There is your vector. Any questions? Did you guys get it working? Would you like me to show you the code again? Does it work? Does it work? Other. Oh. Strange, but it's because you have imported system.numerics. Probably you didn't. Probably the editor dropped that in on you unexpectedly. Basically, it was like there are two definitions of vector tree, one in Unity and another in C# generally, and it was telling you it couldn't decide which one you wanted. So, you get it working? Yeah. Is it working? Cool. Alright. Is it working? Cool. Awesome. Did you get it working? Working. Good. Working? Good. Working? So, so now, let's do a little bit of ray casting then. So with ray casting, yeah, let's do it that way. So with ray casting, you're trying to draw a ray to hit another object. So in order to do a demonstration of this, we need another object, right? So let's create a new object. New 3D object, let's make it a sphere. Put it at some distance to your other object. Doesn't have to be a sphere. Now, to this component, please add another script. New script, let's call this orbit. Double click on it, and you edit. So, this will be another fun little game, a fun little example, also pushing on this kind of geometric stuff. So our object with this program is to make it so that our sphere object travels in a circular path around our other object, or kind of incidentally around the other object, around a point. We want it to move in a circle, right? The manner in which we accomplish this is using some trigonometry. So, in order to move in a circle, we need to know two things. Number one, what angle are we currently at? And number two, what is the radius of the circle that we are traveling? So, let's make those public variables. If you're getting the impression game development requires geometry, you are correct. It requires quite a lot of geometry. So, public float, not flayop. If I had a nickel for every time I had written flayop, tour, or place, man, I would be rich. Radius. Public. Also, pulpit is another one. Public float theta. Good. We will also, so as things keep going, we will need to adjust our theta over time, right? Because the theta is telling us what the angle is through the circle. That angle should be increasing over time, right? So, in update, let us set theta is equal to, theta plus equals orbital speed, which is a variable I'm about to create, public float orbital speed. There we go. So, now we need to calculate the position of the sphere in two-dimensional space based on our radius and theta. Does anybody need the board? No? Okay. So, if we have a circle with a center point, with some radius r, and some angle theta, and we wanted to find the x and y components of this point, x and y, how would we do it? That will be y, and this will be x. R and theta are known. How do we calculate x? Reach deep back into your brains to grade 10. I don't know, did they still do trigonometry in grade 10? Yeah.
Use cost, right?
Yes. Remember, SOHCAHTOA, right? To find x, we have, so hypotenuse, opposite, adjacent, right? X is the adjacent angle, there we go. So What's the formula?
Cos theta equals
So in this case, that would be, since the hypotenuse is the radius, and the thing we're solving for is x, how do we rearrange that to find x? Yes?
Hypotenuse cos theta.
Right, you bring that to the other side, so r times cos theta is our formula for x. And similarly, because y is the opposite rather than the adjacent, r times sine theta is equal to y. Now that we have our formulae, all that remains is to write a program to calculate these formula, calculate our results. So, but for us, it's not going to be the xy plane, it's going to be the xz plane, because like the ground in Unity is the xz plane, because y is height. We could use a different component. In your own programs, feel free to use whichever two components you wish. You'll get like different orbital patterns, but I'm going for one that goes like this. All right? So, float x is equal to radius times. Now here's the question. Here's the million-dollar question. How do we access cos and sine? Haha, no. I mean you can, but you can just also type math f. So math f, in the same way that vector 3 provides a bunch of stuff and color provides a bunch of stuff, math f stands for math function. So that's where you get all of your different mathematical functions, which are actually tied to kernel. So, for example, exponentiation. Or, you don't have to worry about or logarithms, min and max, ping pong. Round to int. There's sine. So we said a sine is inverse sine, it's arc sine. So, sine theta. This should work, right? Wrong! Read carefully. F, the input angle in radians. Dun 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 dun. So, this is actually not a problem if you just think in radians, but you guys have done radians before, right? You know what radians are? Yes? No? Come on. Give me something. Do you know what radians are? Yes?
It's like a really short. It's like if you broke up a circle of 360. It's like,
Yeah.
So it's like pretty short. That's where that
If you replace 360 degrees with this, you get radians. What is this? What number is this? Close. 2 pi. So if here you have 0 degrees, 90 degrees, 180 degrees, 270 degrees, then in radians you have 0, pi by 2, pi, and 3 pi by 2, so slash 2 pi, slash 360 degrees, right? Radians. So we have to convert to radians, assuming that our theta angle is in degrees, which everybody likes degrees. Let's assume that theta is in degrees. In fact, let's just comment that in degrees. Because you guys are doing a degree, right? Math F dot degree to radian and radian to degree. Ooh, nice. The math function library contains conversions to and from radians. Of course, you can also just use the formula, which is if theta is in degrees, the first thing you have to do is divide by the total number of degrees that exist by 360, and then multiply by the full go around in radians, which is 2 pi, so that becomes theta times pi over 180, and that is the actual way that you convert between, and then just invert that if you want to go back. But yeah, why do that when you can have a math function? Degrees to rad, which is absolutely rad. Why is that not making up? Dang it. Oh, is that it's a constant, isn't it? Yeah, okay, so you have to multiply it. It's not a function, it's a constant. By the way, if you want pi, you should go to the cafeteria. Whack! Mathf.pi. There you go. So then you can throw in your z. All you have to do is replace sine with cos, and Bob's your uncle. So, having calculated our x and z positions, all that remains is to apply these variable values. Sorry, let me scroll that up for you or folks in the, what is only the third row. This really, I was really optimistic about this room, but this seems to be a persistent problem, you know? The screen is too low. That light is too low. If the light were higher, we could put the screen higher, then you'd be able to see it. Anyway, we want to apply these new components to our position, right? So this dot transform dot position, you can assign to this, but you have to assign a vector 3. Now, we don't necessarily want to create a variable for this. We can create a new vector on the fly every frame and just plug it in. New vector 3 x, comma, 0, comma, z. Question?
We have to, at any point, put in an actual unit for orbital speed to start. So it's orbital speed and theta both currently don't have anything.
I was going to play with those. Because I made them public, I'm going to play with them in the editor. And that's actually something I recommend that you do if you're, if you ever find yourself actually using these skills and making something in Unity. We have developed the system that will do what we want, we hope, but trying to estimate what the correct radius is going to be is difficult. Better to just look at it as it operates, as it's simulating, and then use numbers that look like they make sense. So, let's save. Anybody still need to see the code?
Understanding.
Okay.
That's fine.
Alright. I will give you 10 seconds. Alright. Now. So we're running this thing. Can we see anything yet? And you please work? Oh, where's our little sphere? It's disappeared. What's actually happened, it is perfectly contained. Oh, wait, it is gone. Oops, it's gone entirely. I added it in play mode every time. Yeah. That's easy to reconstruct. Create your sphere, attach your orbit script. What a pain. There you go. So you can see with the orbit script, we now have radius, theta, and orbital speed as exposed components. So, so when you make something automatically in Unity, it'll drop it into the center of your scene view. Let's just zero out those components. 0, 0, 0. There we go. And you can see that our cylinder does actually have a little bit of sphere poking through in the rendering. What do you call this when a video game does this? Clipping? Yeah. Or tearing. This is called tearing. So, there we go. Our little thing is not doing anything at all because we have not specified an orbit or an orbital speed. So let's try one. Let's try an orbital speed of this is degrees per second. So let's try 0.1. And let's try a radius of 2. Not bad, right? And you can modify your orbital speed. There you go. Pretty good, right? Did you turn it up so it's like yeah. 100,000. Oh, okay, actually here's an interesting thing. Okay. So okay, let me show you something cool, another cool math thing. So here, things obviously are like just slowly crawling along. What happens if I increase the speed? Here it is at 1. Right? 2, 3, moving much faster. 4, 5, 6. Here, it becomes much easier to see the individual frames. Right? You can see how it's rendering each of the frames now, right? Because it's moving. The faster it moves, the more it sort of destroys the illusion of animation. Let's try 10. So now you can see that it almost appears to have static positions, right? It's 360, so in theory, if you do something that's divisible by 360, you should get something like a standing pattern, right? This is called aliasing.
360.
Well, yeah, because it's jumping to the same point each time, right?
Oh, it's like kind of fidgeting.
Yeah, right? Because it's jumping between 2 points. You get the illusion of having like 2. But if you do something like 79, you know, you can have the illusion of movement in the opposite direction, right? this illusion of movement in the opposite direction is actually what's meant by the term aliasing. Right? Not to get too heavily into it, but, since I'm having fun, this is what happens, right? It has to do with the sampling frequency of an oscillating signal, right? So if you sample an oscillating signal fast enough, you can perfectly reconstruct the original signal, right? But if you're not sampling it fast enough, basically, if you try to reconstruct the wave, you get a different wave than you originally had because you're not sampling fast enough. Turns out that you have to sample at least as fast as half the frequency of the wave in order to be able to reconstruct the signal. This is actually called the Nyquist frequency, or the Nyquist limit. But, so there you go. Question?
So the orbital speed is it?
No, orbital speed is in degrees per frame. And then this guy is in just degrees. Because we're converting, the trig functions require radians. We're performing conversion to radians from degrees. We could just keep that in radians if we wanted to, but who wants to use radians? But yeah, does that make sense? So, if you turn that off, let's just give it some nominal values. Give it a 1. There we go. So now we don't have to re-enter those values whenever we turn it on. There we go. So, now, let's perform a raycast. So, this is not this one. All right. So, raycasting is something that's performed by the physics engine. Physics dot. We have all of these physics functions. A lot of them are very complicated and we shouldn't have to worry about them. But very important is the raycast method. If we take a look at our suggestion usage, we have, similarly to the debug ray, an origin vector, a direction vector, a max distance, and then a couple of optional ones we don't have to worry about. Okay? As you can see, 15 overloads. That means there are a lot of different ways to call this method. So, there we go. So, let's make the origin of this raycast, again, the center of the object that the script is attached to. this dot transform dot position. Direction. Now we need to decide. So Unity transform objects provide a few pre-baked vectors that are just automatically provided for objects. So it's kind of a bit silly as like a cylinder doesn't necessarily have a forward, you know, because it's round, it's symmetrical. But if you imagine you had a little car, right? Okay. You have a forward vector. You have left and right vectors. You have up and down vectors. These are designed to be tied to the car's geometry so that if the car is moving in space, the direction that the forward vector is pointing is modified as the car is moving, right? So it's relative. The forward direction is relative to the position of the car. All right. So this dot transform dot forward, for example. And this raycast is going to be invisible. So a thing that we can do, if we're interested, is to draw a debug ray with the same vector, this dot transform dot debug, or transform dot forward. Make the color blue, sure. And because forward is a normalized unit vector, to give it some length so that we can see it, let's multiply it by 20. And duration shall be a really long time. So back to our raycast. Max distance. I believe if you leave it off, it just goes off to infinity, which is fine. We don't have to specify a max distance this time. Make sense? Cool. So the question then is, if we are performing this raycast, what information is this operation returning to us? Well, for the information on that, let's check the documentation. Physics.raycast returns a Boolean. So it returns a Boolean based on whether or not the raycast hits something, right? So if this raycast is true, debug.log hit. Else debug.log miss. Shall we see if it works? Or you guys are still copying it down here? I appreciate your like positional preference, but I just feel that it's only fair to say I got like a whole bank of computers in the front of a room, and you guys wouldn't have to be popping up and down all the time if you used them. Just saying. Feel free to sit where you want. Okay, let's see if it works. Collapse. There we go. So, relative to the camera, forward seems to be pointing in that direction. So you can see when the sphere passes behind the cylinder, our hit goes up about 30 each time, and our miss is constantly going up unless the thing's behind it. So this is fine. This works, but it's just not fancy enough. This is a little hard to pick out. Let's use some of our knowledge from last week to make things a little prettier. Maybe the cylinder changes color when that sphere is inside of its zone of detection. In order to do this, the cylinder will require a material other than the default one. So, you create material, there we go, new material, good. Let's make the default, we won't even need the default, but let's call it something. Rename. Cylinder. Apply the material. Materials, cylinder. Good. So using our knowledge from last week, this .GameObject .get component mesh renderer dot material, the first one, dot color is equal to, let's just say color dot yellow, or what color should it be on hit? Red. There we go. And on miss, let's make it green. Yeah. So, let's save that. I think I'm just gonna like move the camera a bit so that it's not perfectly straight on. Down. There we go. Out they go. And just to prove it, remember this this blue line is the raycast for that's being used to determine this outcome. If we take the sphere and just slow her down a bit. Right? Fine? Sound good? So, any questions? Do you want to see the code?
I want to see the console.
Console? Sure. I didn't remove the debug messages, so they're still going.
How did you?
Oh, how did I do that?
Yeah.
Collapse. That's much better, right?
Also, the blue line is not.
Oh, no, that was the duration that you did. Go back to your code. Multiply this vector by magnitude of 1. So I used 20. Did you get it working? Nothing? I noticed that you don't have the sphere object. That would help right there. So, create 3D object, sphere. There she is. 0 position. 0 position of your cylinder. Let's go at it. There we go. Sphere, we attach the orbit script, like so. Pick something reasonable, radius of 3 maybe, and speed of 3. Now, you'll notice that you are rotating in the XY plane, which is fine, except your forward, yeah, I think we'll still cross your forward, so that's fine. The reason it's, for me, it's rotating this way is because I chose the XZ plane for it to orbit. But this is fine. Now, let's see here. Yes, you're missing some code here. Yeah. I'll put the code back there. You should make more progress now.
This one.
There we go. Working? That looks working to me. There you go. Long day?
Just kind of
Ooh, that's not good. Yeah, these aren't fantastic chairs for back injuries. Yeah. Well, you're young. You'll recover. All right. So. And now for something completely different. cover switch cases. So, we are done with Unity for the time being. Although, yeah, I can still demonstrate using Unity. So, let's see here. How can I modify this? Let's make a new script and attach it to okay. Now we'll go from where we are. Okay, so I am going to write some code which counts the number of times that this that the sphere object has entered our raycast area. Note, this is different from the number of raycast hits. Depending on the speed of your object, you can have anywhere from 10 to 100 raycast hits for any particular object. Right? What we're interested in is the number of times that object has entered the region. Okay? So, let's make a new public integer. Hits. There we go. And a new public boolean, or just bool. There we go. We will call this as sphere, or as target. That works better. So, we are going to use this Boolean variable as a flag. A flag is something that indicates some state of the program, and it's like if something happens, you raise a flag. If something happens to reset the flag goes away. That's the idea of the flag. So, as target will initially be false. False. If our physics raycast hits the object, we will say as target is equal to true. And when the object is no longer there, as target is equal to false. So this Boolean variable currently keeps track of whether or not the raycast has hit something. You may say to yourself, well, aren't we doing the same thing here? And the answer is, well, you don't want to calculate your raycast every time, do you? Obviously not. So, here's the thing though. We want to do something different the first frame that the raycast hit happens. Right? So, if does not have target, not has target, then it's plus plus. So, as this program executes, if we hit this case and has target is false, what that means is in the previous frame we did not have a raycast hit. This means that if has target is false, this is the first frame of the hit. We then immediately, as soon as we execute that, turn has target to true. That disables this if statement until a lack of a raycast hit resets it back to false. Save, 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 save. So we can watch the operation of this. Take a look at our inspector. You can see has target blinking in and out, corresponding with the material turning red. And you can see that number of hits is working. Increasing once every time the sphere enters the target zone. Does that make sense? Now, my object is to do something slightly different, to have some kind of oscillating behavior, to do something slightly different depending on the number of hits. What I'm going to do is I'm going to change what color the mesh renderer gets based on the number of hits that I've had. So, if, I'm going to use this if statements for this first. If hits is equal to 1, let's define a color variable. Color temporary is equal, is nothing. If hits is equal to 1, I'm going to use the temp is equal to color dot white. Else if hits is equal to 2, sorry guys, temp is equal to color dot magenta. Else if hits is equal to 3, temp is equal to color dot cyan. There we are. And instead of writing red here, we write temp. Further, just so that I get the oscillating behavior, hits is equal to hits modulo 3. So anytime hits becomes 3, it gets reset to 0. So it will count 0, 1, 2, 0, 1, 2, 0, 1, 2. Oh, I'll modify those so that it's 0, 1, 2. Technically speaking, you only have to modify the color once. Like I'm doing too much work here. Technically speaking, you only have to modify the color once when you enter the region or leave the region. So this is overkill because we're writing it every single frame, but whatever. Why do you hate me? Use of unassigned local variable. It's not unassigned. Oh, it might be unassigned. Okay. Default color is clear. There we go. Let's see how this works. Purple, cyan, white, purple, cyan, white. Okay, so the if statement works. Let me show you a slightly more efficient, but really just different way of expressing the same code. When you have a series of equality comparisons like this, where you're testing this, 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 you can substitute an if statement, if else if block for something called a switch statement. Switch case. In the brackets, you put the thing you are switching on. In this case, it is the number of hits. You then write cases. Case 0, case 1, case 2, and then you can also add a default. You also have to include breaks. Otherwise, execution falls from one case down to the next. Who does that? Just walks into a classroom like that. Like, come on. I'll tell you one thing. My wife is hearing about that one over there. And then it's like, he gets offended when I say, hey, you're interrupting a class.
What the door is like.
The door wasn't wide open.
Correct.
Like, so anyway, if you run this, switch cases work the same way as if statements. So a little birdie tells me that basically one of the things you have to do in the lab on Friday is to write some code and then write the same code for a switch case. Like do an if statement version, then do a switch case version. So hopefully you can pick up on the similarities here. Basically, in order to transpose code into a switch case, you take these guys, you make those your case labels, right? You take the lines inside, you put them inside of the cases, and you have to include breaks. Default isn't doing anything, so it could be removed. Does that make sense? Hopefully, maybe a little bit. You should try it out. Do some practice. All right. Any questions? Yes?
For the last lab, you said that you made the due date Thursday, but it says that Sunday. That's Sunday 22.
Well, let's just take a look, see, shall we? I try to keep my passwords over 30 characters.
I got this.
Assignments. Edit. Thursday. There we go. Thursday midnight, or 1 minute before midnight, because I think midnight Thursday is actually like 1 minute after the last minute on Wednesday. Because midnight belongs to the new day, I'm pretty sure. So Thursday at 11:59 p.m. So there you go. The due date is now correct. Please have your labs in by the due date, as it has now been corrected. Any other questions? Power Lab 1 is coming along. I see I got 2 submissions out of 8. Hmm? Okay, well, just, get them in. Oh, is he? Video game development or video game design? Yeah, because those are 2 different things. Yeah, that's a new one. I'm actually, I have a passing friendship / acquaintance with Raphael, who's the director of this program. Yeah. Yeah, he's a cool dude. Yeah, when you run a video game development extracurricular club, you start to network with these types of people. Yeah. Okay. Well, I don't really have anything more to say this evening, so I think I'm going to let you go a whole 1 minute early. There you go.
Can you share the codes?
Yeah, I'll share the code.
I am not getting a double.